Hello, welcome. Today, my partner and I, Brendan Messier and Taylor George, will be talking to you about a pool skimmer that we are contracted by Microwire Systems Incorporated to design and make. A little bit of background. If any of you have pools, especially here in Vermont, you know that the leaves can become quite the problem, especially around autumn foliage season. Also, you get a lot of bugs, frogs, pine needles, everything else, scum, just basic scum on the surface of the pool that you always have to clean out, maintain a good looking pool. Now the issue with that is actually getting out there to do it. Okay. A few of the existing technologies, of course, is a manual method with just a regular pool skimmer, or there are automated pool skimmers. A few of the existing technology designs. One of them here is fully remote controlled. It's relatively cheap at $100, well, cheaper than the other one, though it is time consuming due to the fact that it is only remote controlled, though I suppose it would be quite fun to motor it around in the pool. It also has good navigation because you yourself can use it to chase down any debris that happens to be in the pool without any preset navigation. Whereas the second one is $500, quite a bit more expensive. It's solar powered. It is also fully autonomous, but the way that it works, it uses these moving wheels on the edges to navigate and rebound off walls, which tends to let it get stuck directly on the walls and just run along them without actually getting into the center of the pool, where the doldrums tend to be and a lot of the debris collects right in the center. Also, it's very slow. Its method of propulsion is a paddle wheel, which does not propulse it very quickly at all. Our proposed solution would be a very low cost, preferably lower than the remote controlled device, but quite a bit cheaper than the regular fully autonomous one, which we hope to mirror more closely. It has to have efficient navigation, but fully automated navigation so that it doesn't stay directly on the edges or in the center. It can go everywhere and anywhere, and it collects from the entire pool regardless of pool size or shape of the pool. Also, one of the other things that we would primarily like it to be is a do-it-yourself put-together kit so that you can just go to the pool store and it's small. The pieces are easily replaceable, and it's very easy to put together, which also reduces costs on manufacturing and assembly. Some of the required features of our proposed solution would be that it is fully autonomous, that you can just set it in the pool, and it automatically does whatever it needs to. It has to navigate both the center of the pool and the edges so that it gets things stuck to the edge of the pool. It also gets things just sitting out in the middle. It has to be self-calibrated, meaning that it automatically takes into account the size of your pool to decide how it will navigate and therefore adjust its timing delays and such so that it will come off of a wall and go all the way back into the center before it turns around and goes back to the edge. It has to be easily retrievable, meaning that at the end of its run time, it goes to a side of the pool and it stays there. That way you don't have to take a manual net or anything to try and fish it out of the center of the pool or anything like that, or chase it around, whatnot. It'll stay where it is at the end. It has to clean easily. One of the drawbacks of the other two designs were that you have to take them apart to get at the net that is internal. So we really want it to be able to, once it is finished cleaning, you take it out of the pool and you just remove a net or some other device so that it can easily be just dumped in the trash and put back in, clean, easy. Also, we'd like it to be entertaining, much like the remote controlled one, except in a different manner. We were thinking of a party mode, where it uses underwater LEDs to illuminate the pool with various colors at nighttime, which makes it enjoyable. It also will tell you when it's finished through the lighting. Some of the main system components that would be required in such a kit design would be a Kinetis board, a microcontroller that we would use to handle all of the inputs from sensors, the light sensor, accelerometer, everything like that, and also the outputs to the motors, turn them on and off. Would use pool noodles as the primary buoyant device. That way the kit can be made that much smaller and easier, where if you're buying it, you'll go into a pool store and the pool noodles will already be right beside it, so it'll make it very easy. You can also customize the colors and whatnot. The net is the most primary of the components because it is what actually picks up the debris and contains it during the run cycle. We're going to be using two 12-volt DC water pumps as propulsion, a 12-volt battery to power the kinetis board, the pumps, the lighting, everything that needs to be on board. It's also rechargeable and long-lasting battery life. We're using an onboard accelerometer on the kinetis board to handle all the impacts of the walls to determine whether or not it should start turning away from the wall to go back to the center, which is handy that it is directly on the board. We want an airtight box to contain all of the electronics that are not waterproof. The LEDs and pumps are completely waterproof, so they'll be on the outside, but all the kinetis board, internal electronics will be inside there. And then there are the LEDs, which will be adhered onto the outside of it to provide the subwater water illumination. Here's the general system diagram of it all. The pool noodles on the sides acting as pontoons and supporting the entire craft. The net right in front. The pumps will be placed underneath, below the water line, and wired to the kinetis board. They'll be pulsing out the back so that the net is always facing forward and always collecting debris. The LEDs will be on the side right here or on the bottom to illuminate the bottom of the pool primarily. And the on-off button, kinetis board, 12-volt battery, light sensor all will be contained within the waterproof box, which we have right there. And that is the entirety of it. Okay. From the side view, here is the net here, which will be catching all of the debris. It's oriented so that the water line is primarily right at the mid-level, so that debris floating very high on the surface, such as very light maple leaves or anything floating slightly below the surface, pine needles, bugs, whatnot, will all be caught equally as easy. And that way it won't run into either of the top or bottom pieces of the net and the skimmer. Also, the pump is located at the very back there. We'll have a bottom-facing intake and a rear-facing outtake used for the propulsion system. The buoyant force is one of the primary components of the engineering. That way we can orient the water level approximately right in the middle, as I previously mentioned. And through calculations here, we measured and calculated the weight of the device to be about 5 3/4 pounds, a little bit heavier, a little bit lighter, right about in there. And we came up with a displaced volume of it being 0.0026 meters cubed, which equaled out to just 880 thousandths higher than perfect midline from bottom to top. And that way it is very close, and whether or not we add a little weight, lose a little weight, it's going to stay quite there in the center. One of the main challenges we faced, or decisions that we faced, was how to orient the pumps. One of the concerns here was that small debris that would hit the net and keep going through, such as these pieces here, would somehow get caught or clog the pumps and therefore negate the effectiveness of the device. So we decided on right angle pumps. And that way they suck from the bottom, avoiding all of the debris that might come through or around from the sides. And it gets a clean water supply going in. And then it propulses directly out the back, which will speed these smaller particles away from all of the other pieces. The mechanical design here is general SolidWorks model, and Taylor George will be talking more about that.
For this project, we use SolidWorks, which is a 3D CAD modeling system. And here you can see a model of what our product looks like. The main component is the frame, and it holds everything together. It's made up of two unique parts, one being a ring and the other being a side rib. And now, because we wanted this to be a kit, we wanted everything to snap together really easily so that everyone could put it together and not need a lot of tools. To do this, we had a feature called a snap feature, as you can see here, where a part of the rib goes through the ring and snaps it together. This is a picture of the ring. It's actually half. It's two halves that come together. They're identical. You just flip one and snap it together. It has a hole here where you can see the other part of the rib will come through. And here's the rib. It's got 4 flanges, 2 for each ring. And they go down in and deflect 14 thousandths, I believe. 40 thousandths. And that's shown here. There's a little lip on the end of the flange that will deflect as it goes through and then snap back over the edge here. That holds everything together. We decided that we needed that flange to be thin enough so that it didn't require too much force, but thick enough so it wouldn't snap. At 20 pounds flex force, it would be able to deflect that 40 thousandths, and that was a good amount of force. For the ribs, we needed to make sure that they were sturdy enough to not bend in the middle because they're quite long. With 20 pounds of force pressing down on the top, you can see here, without a I-beam, it would deflect 150 thousandths. So what we did is we added one, and there was quite a difference, as you can see here, minimal deflection of 19 thousandths. Our electrical design is here. We have the Kinetis board shown here with all of its ports. We have our battery hooked up to a main power switch, which turns on and off everything. We have a photoresistor, which is our light sensor, and it will tell whether it's light or dark out. We have the battery powering several LED strips, and we also have the battery powering 2 pumps, which is our propulsion system. When deciding what kind of battery we needed, we had to add up all of the requirements from the different components. We had 500 milliamps being drawn from both pumps. We had 400 milliamps from the LED strips, and that totaled 1400 milliamps. We wanted our product to run for about 2 hours, so we had a total battery requirement of 2800 milliamp hours. And so we purchased a 6800 milliamp hour rechargeable 12-volt battery. For our programming, it starts off with a calibration cycle, where it will go forward until it hits a wall. This tells you the longest distance it can travel in your pool. It'll then cut that distance in half so that it will tend to navigate halfway to the middle of the pool and center itself. Once it's calibrated, it will go into a routine that will cycle between going forward and either hitting a wall and turning around, or going forward and timing out and turning around, so that it will stay in the middle of the pool as much as possible. This entire cycle will also be checking constantly how light or dark it is outside, so that it can turn on or off the LEDs. After it's reached its 2-hour runtime, it will go into a home state, which will have to go straight into a wall and stay there for easy retrieval. Our work breakdown structure is shown here, with the tasks on the left, who is assigned to each task, when the due date is, and whether or not it's completed or not. Our upcoming milestones start with the completion of all wiring. That's scheduled for April 8th. Next, we will do a final benchtop test of all systems after they've been wired together. This includes pump control, light detection, LED timing and control, accelerometer functionality, and lastly, battery charging. This is scheduled between April 8th and April 15th. Lastly, we will do a final pool test of the main program. This is scheduled for April 15th. Our budget, so far, has cost us $144. This does not include a lot of the plastic pieces which were printed on a 3D printer by Microwire Transmission Systems. This was absorbed and reduced our budget significantly.